Free body diagrams part 2. And just to remind you that free body diagrams, force body diagrams are all just identifying the forces that are acting on the object. So let's refresh our memory about the different types of forces. Basically, we got these 4 specific forces. We've got gravity or weight that's always acting down, the normal force, which is always perpendicular to any surface the object might be touching, tension, which is a force in a rope, string, anything like that, and then friction if there is a force between 2 objects as they're rubbing against each other. Okay? Some scenarios may not have a force due to friction if friction is negligible. So that one shows up every now and then. But if it's just a generic force, we just name it F. So what's new about this one? Well, in the previous video, we've talked about forces that are just right and left, up and down. Not every situation is like that. So sometimes we get vector components where this force is acting at an angle, so some of that force is actually being directed sideways while another part is being directed up simultaneously. Now we don't draw the vector components. We only draw the main vector itself. But the size of these components may play a factor on how big we draw other vectors. Okay? Now mathematically we can actually figure this out, because to figure out this side, well, we would use sine. Let's call that one R. And then to find this one, let's call it X. We would use cosine. Now we'll get into the math later on in a different video. But keep in mind that if something's at an angle, not all the force is going to act in just one direction. On our force diagrams, we need to make sure we only draw the main force and never, ever draw the components. So let's look at a few. We've got a box that's being pulled by a rope at an angle above the horizon. Usually we always have these angles above the horizon, whatever that is. Okay? And so we need to draw the free body diagram for this one, and it states that there's no friction from the table. Well, we always have gravity acting down. That should probably be one of the first vectors you draw. We have the normal acting up. But notice I didn't draw it quite as big as I did this one, because we've got this force right here that's pulling this direction. Again, your free body diagram should accurately show the direction and amount of the forces acting on the object. And so since this one's up being pulled by a rope, we're going to call that a tension. So we're not going to worry about specific sizes now. If we had a grid, we would do that more. But between this one going up and the part of this that's going up, that should equate to how much this is acting down. The combined nature of these two counteract the weight and keep it in the same spot that way, although it's accelerating to the side. Let's look at this one. It does have friction, so it's moving at a constant speed. So again, we'll have weight acting down, the normal acting up, and again, I want to make it slightly smaller because we have this force pulling at that angle. Try to make the angles as similar as you can, but they're not going to be perfect unless you use a protractor. That's a tension. So the vertical part of this and the vertical part of this should counteract that. But we've got a horizontal force. And it says it's moving at a constant speed, so that friction needs to counterbalance this component of that tension. And so I'm going to make it, essentially try to make it the same length and call that the force due to friction. Again, it's more important to get it labeled and the arrows drawn in the right direction. We can work on the size later on in a different video. So what about this one? We've got a person holding on to 2 ropes, maybe like a gymnast. Now, even though he's not touching the ground, gravity's still going to affect him. So gravity's still going to act down. But he's holding on to 2 ropes. So we got one rope going this way and one rope going that way. It should be about the same length because it makes similar angles. And the upward force of this one, the upward force of that one should balance those out. But we got two ropes, so I'm just going to call this T1 and T2. Really doesn't matter which one you called 1 and 2, just as long as you have different designators for each one, because they should be the same, but they may not be. We can look at those later. Like on this one. This one we got another person hanging from two ropes, but now they're not making the same angle. These two should be the same angle, and these two tensions should be the same, but here they're definitely not. So again, we have gravity acting down. First one you should draw. This one should be more straight up, while this one is more angled out. This one, I probably drew a little bit too long, but that's okay. We just want to concentrate on direction right now. Let's look at some more free body diagrams. Again, just mainly focusing on the direction and naming the vector. All right, so we got a series of boxes on ramps. So we have gravity acting down on this one. It is a box sliding down a ramp. The friction between the box and the ramp is negligible. So that means we don't have to worry about friction. So we got gravity acting down, but it's touching a surface, so we need a normal. The normal would not be acting straight up because the normal is always perpendicular to the surface, so it should be going this direction. So I want to draw it in here, and that should be the normal. And since there's no friction, that's the free body diagram for that situation. But if we look at this one, now this box is not sliding, it's stationary. Well, if it's on a ramp, it should slide down. So there's got to be some force holding it back. So this one does have friction, simply from the situation that it's in, because it's stationary. So we have weight acting down. We have our normal force acting this way. And then we'll have friction, and friction is going to act against what motion should be there. So it's going to act back up in this direction. That will be the force of friction. And usually there's a 90-degree angle between the normal force and the force of friction. That's one way that you can use to kind of gauge your picture. This one, again, stationary, but it's being held by a rope. Well, we still have gravity acting down. We still have the normal going this way because it's perpendicular to the surface. And it's stationary, so this rope's holding it. It looks nearly the same as that one, but this would be a tension, not a friction. There may or may not be friction here. We don't know because it's not really needed. That rope is going to hold it in place, and so we don't need friction. This could be a frictionless surface, or it could have a lot of friction. But it's the rope that's actually going to hold it in place. Let's look at this box sliding down a ramp at a constant velocity. Again, if it's sliding down a ramp, if gravity's the only force acting on it that's causing it to move, it should accelerate. But since it's moving at a constant velocity, that means that there's got to be some type of friction acting on the object. So we got force of gravity acting down. This one I want to have the normal kind of go more this direction because again it should be perpendicular to the surface. And friction should be back up this direction. It should look like that. So a lot of these force diagrams look very similar depending on the situation. The only difference is how long we make these and what do we name them. Thank you. Next time we'll talk more about vector components, how to use them, how to gauge the size of these vector arrows that we're going to use. Goodbye.